Hello everyone and welcome to this video. Today we're talking about the concepts under magnetic effect of electric current. Now as the name suggests, we're trying to find out if the electric current has a magnetic effect. So far we have learnt about charges and we have learnt about the electric current. But now I'm going to say that the electric current has a magnetic effect. Now actually this is a very wonderful story. Because earlier they thought that electricity and magnetism were two different things. So they studied it as two different subjects. There was a different theory for electricity and a different theory for magnetism. Till Oersted came along and said that these two could be related. And we did this with the Oersted's experiment. And then we saw that electricity and magnetism are not two different subjects, but in fact they are related to each other. And this formed the new subject of electromagnetism. And then we realized that electric and magnetic fields are basically the same thing. So let's start with this wonderful experiment that changed the course of history, where electricity and magnetism became intertwined forever. So what exactly did Oersted do? Basically, he was preparing for a lecture, and on his lecture table there was a straight current carrying wire. And next to that wire was placed a magnetic needle. And he saw that this current in the wire is noticeably deflecting the needle in the compass. Deflecting the needle means that because of the current in the wire, the direction of the needle was changing. And then he realized that why is this happening? He started asking himself this question. And then he started to study this phenomenon. So he saw that a current carrying wire was basically affecting a magnetic compass needle, and he tried different things with it. One thing he did was that he reversed the current, and he saw that if you reverse the current, then the direction in which the magnetic compass is deflecting is changed. That is, it goes in the opposite direction. So he realized that reversing the current will reverse the direction in which the magnetic compass needle will move. And then he did something else. He changed the distance between the current carrying wire and the magnetic compass, and he saw that if you increase the distance between the compass and the current carrying wire, then the amount of deflection will decrease. So he saw that the distance between them also affects how much the magnetic compass needle is moving. And this is how he studied the relationship between the electric current, that is the current carrying wire, and the magnetic compass needle. So here even you and I can think what exactly must have happened. We know that only magnetic fields can affect a magnetic compass. And if an electric current is affecting a magnetic compass, it must mean that the electric current also produces a magnetic field. And this is exactly the conclusion that Oersted came up with. He said, just maybe the electric current carrying wire is producing a magnetic field. And then we tried to find out what this magnetic field looks like. Now we know that there are two ways to look at a magnetic field of a current carrying wire. One of the most famous ways is to sprinkle iron filings around a straight current carrying wire and see how they arrange themselves. So you basically have this straight current carrying conductor, and you place iron filings on a sheet which surrounds this conductor, and you lightly tap this sheet and you will see that these iron filings arrange themselves in concentric circles. So this is what Oersted saw as well. Oersted saw that when he sprinkled iron filings around a straight current carrying conductor, they arranged themselves in concentric circles with the wire at the center. And these concentric circles are exactly the picture of the magnetic field. These are the magnetic field lines of a straight current carrying conductor. So Oersted concluded that moving charges, that is currents, must be producing a magnetic field. Remember, electric field is generated by stationary or charges at rest. So electric field means charges at rest, stationary charges, but a magnetic field means the charges are moving, that is basically a current. So currents produce magnetic fields. Now, as you can see, I have drawn some directions to this magnetic field. We'll see in a minute how to find out what is the direction of a magnetic field. But this was the first way to find out the magnetic field of any kind of a current carrying conductor. He also saw that the alignment of the magnetic compass needle is tangential to an imaginary circle which has the straight wire as its center and its plane perpendicular to the wire, which means that this magnetic field is actually at 90 degrees to the straight current carrying wire. So you can see that the plane of the magnetic field is at 90 degrees to the current, and that's exactly what Oersted observed as well. And then he saw that the other way to find out what the magnetic field looks like is to place a magnetic compass near the current carrying conductor. And he saw that the compass needle was actually pointing in a direction which was tangential to the point where you place the needle, and therefore we see that the magnetic field is actually tangential to this imaginary circle, and this imaginary circle is nothing but the concentric circle of the magnetic field. And then you can see that by joining all these tangents at different points, you can recreate the magnetic field, and this is the second way of drawing the magnetic field lines. So this is what Oersted discovered. He discovered that a electric current, that is a moving charge, can generate a magnetic field, and this is Oersted's experiment. Finally, I want to tell you about this convention that we follow. You see, every time you see a magnetic field coming out of the plane of the paper, for example, here we have placed a plane of paper right in the middle of this current carrying experiment. So you can see that the magnetic fields are coming out of the paper, and therefore in this case we will denote the magnetic field with a dot. So you see a dot, it means the magnetic field is coming right at you, coming out of the plane of the paper. And whenever the magnetic field is going inside the plane of the paper, here you can see that the magnetic field is going in the plane of the paper. Here you denote it with a cross. So this is the sign convention that we'll be following, that if you see dots, the magnetic field is coming out of the paper, and if you see crosses, the magnetic field is going into the paper. Now, charges at rest or static charges produce electric fields, which we have seen earlier. And just now we learned from Oersted's experiment that moving charges, or you can say electric currents, produce a magnetic field. Now, we had defined an electric field of a charge by saying that it is the space around a charge in which the effect of the electric field is felt. We'll define something similar in case of the magnetic field. Here we say that the magnetic field is the space around a current-carrying conductor, or it is the space around a magnet in which the magnetic effect is felt. So here you see we have defined the magnetic field very similar to the electric field. But it's very important to note that the magnetic field is a vector field, and it is denoted by the letter capital B. So let's think about how we found out what is the formula for the electric field. When we were trying to find a formula for the electric field, first we wrote down a formula for the force between two charges, and then using this formula for the force, which was the Coulomb's law, we then found the formula for the electric field. That is, we can find an expression for the field by first finding the expression for the force, and we will adopt the same procedure in case of the magnetic field. Before we can write down the formula for the magnetic field, we have to first write down the formula for the force experienced by a moving charge in a magnetic field. So let's start with first finding out what is the force experienced by a moving charge in a magnetic field. So we say that a moving charge experiences a force when placed near a current carrying wire. So see how we can point by point we can compare what is happening in the magnetic field to what happened in the electric field. In the electric field, we said that okay, if you have a charge and you place it in an electric field, then this charge will experience a force. Here I am saying that if you have a current, that is a moving charge, and you place it near a current carrying wire, that is you place it in a magnetic field, then this moving charge will experience a force. And it is observed that positive charges experience a force in a direction which is opposite to the direction in which negative charges will experience a force when placed in a magnetic field. So you see that we have to first find the force acting on a moving charge when it is placed in a magnetic field. So let's try to find out why exactly is it experiencing a force. I mean, this charge is not touching the wire at all. And then of course we learnt that this current carrying wire had a magnetic field, and this moving charge also has a magnetic field, and it is actually the magnetic fields of these two that are interacting which is causing the moving charge to feel a force when it is placed in the magnetic field of the current carrying conductor. Now of course you can ask the question that a current carrying conductor basically has current, which is nothing but charges, and you have placed a moving charge in this current carrying conductor's vicinity. So why can't it be that an electric force is acting between them? It cannot be so, because the current carrying wire is overall neutral and therefore will not exert an overall electrostatic force on a moving charge, which means that the reason this moving charge is feeling a force must be something different. And as we said, it is actually the magnetic fields of these two which are interacting with each other, giving rise to a force which is experienced by this moving charge. So you can see that the magnetic field has many properties which are similar or at least analogous to the properties of the electric field. So some of the properties are very identical. For example, the magnetic field also follows the laws of superposition. So we have not yet given you a formula for the magnetic field, but I am already telling you that it's going to follow the principle of superposition, which means that, for example, if you try to find out the magnetic field at a point P due to 3 different current carrying conductors, then you have to find the magnetic field at P due to the first one, and that due to the second one, and that due to the third one, and add them all up vectorially, and that will give you the total magnetic field at point P. So as you can see, this magnetic field also follows the laws of superposition, that is, it follows the superposition principle. Finally, remember one last point. When a charge is moving, it creates a magnetic field. However, the charge also creates an electric field, because when the charge was at rest, it was creating an electric field. So just because it starts moving doesn't mean the electric field disappears, and therefore we say that a moving charge is actually the source of both the electric and the magnetic field. And when this moving charge experiences a force, and if it experiences a force due to both electric and magnetic fields, then the force experienced is known as the Lorentz force. So what is the Lorentz force? It is the force on an electric charge exerted due to both the electric and the magnetic fields. Together, it is known as the Lorentz force. Now we know that in order to write an expression for the magnetic field, we have to first write down an expression for the force due to a magnetic field. So let's start by first finding out what is the force due to an electric field. This is because the Lorentz force is actually the force acting on a charge due to both the electric and the magnetic fields. So first we are going to recap what is the force due to an electric field. So we have already learned that the force acting on an electric charge of magnitude small q when placed in an electric field E bar is given by the formula F is equal to Q E bar. So remember, this is a vector equation where F and E are both vectors, and you can see very clearly that since there's only one vector on the right and one vector on the left, it means that the direction of F and E depend only on each other. And therefore, there is a straight relation between the force and the electric field. So the direction of the force is the same as the direction of the electric field. And this is a very simple equation that we have learnt about the force acting due to an electric field. Remember, this is the equation when you are placing a charge in an external electric field. But we also learnt about the force between two charges, and that was given by Coulomb's law, and that was 1 upon 4 pi epsilon naught into the product of the two charges magnitude divided by the square of the distance between them, and this was also a vector equation where the direction of the force was along the line joining the charges. So this was the force due to an electric field that we have already found. Now let's move on to writing an expression for the force due to a magnetic field. Now we are saying that a moving charge will experience a force due to a magnetic field. Remember, I am saying that it is a moving charge that will experience a force due to a magnetic field, and therefore if the moving charge has to experience a force, it means that it must have some velocity because it's moving. And it turns out that the force due to a magnetic field on a moving charge depends on 3 things. The first one is the magnitude of the charge itself. So you can see that Q again makes an appearance in this formula. The second one is the velocity of the charge. You see, since only a moving charge experiences the force due to a magnetic field, so its movement, that is its velocity, must have something to do with the force. And finally, it will of course depend on the magnetic field itself, and therefore it also depends upon B. But one very important thing has to be noticed about this formula. Unlike the formula for the electric field, here on the right hand side you have 2 vectors, that is V and B. So here the direction of the force is not so straightforward. In the case of the electric field, the direction of the force was the same as the direction of the electric field, and there was no hassle. However, in case of the magnetic field, there is a particular way in which you will have to find the direction of the magnetic field. The first thing that you have to notice from this expression is that the direction of the force will definitely be perpendicular to the direction of the velocity, and it will be perpendicular to the direction of the magnetic field itself. This is because the velocity and the magnetic field are entering this equation as a vector product, and by the rules of the vector product, the answer of the vector product is always perpendicular to the plane formed by V and B, which means that F will be perpendicular to V and F will of course be perpendicular to B as well. So the direction of the force is always perpendicular to the velocity and always perpendicular to the magnetic field itself. But this does not mean that the velocity and the magnetic field are always 90 degrees to each other. No, the velocity could be at any angle to the magnetic field. And because V and B enter this equation as a cross product, it means that the force will also depend on the angle between them. So let's see how it depends on the angle. We know that F is given by Q, V cross B, and the cross product rule says that V cross B means VB sine theta. That is, the magnitude of the force due to a magnetic field will be Q, V, B sine theta. And as this angle will change, the magnitude of the force will change. So let's try to bring these forces together and try to analyze when will the force be maximum and minimum. Let's say that the angle between the velocity with which the particle enters a magnetic field and the magnetic field is theta. Then let's analyze what will happen if this theta's value changes. We see when V and B are parallel or anti-parallel, the magnitude of the force will be 0. Because when V and B are parallel, the angle becomes 0 and sine 0 is 0, so the force becomes 0. Similarly, when V and B are at 180 degrees, again, the sine of 180 is 0, and therefore, again, when V and B are anti-parallel also, the force will come out to be 0. So we learnt that the force due to a magnetic field will be 0 if the velocity and magnetic field are parallel or anti-parallel to each other. So of course then the next question is, when is it going to be maximum? It will be maximum when the angle between V and B is 90, because sine 90 is 1 and that's the maximum value of that function. So when velocity and magnetic field are at 90 degrees, that is when the particle is entering the magnetic field perpendicularly, at that point the force acting on the particle will be maximum. Finally, let me show you a small way in which you can find the direction of the magnetic field. This is known as the right-hand rule. In order to find the direction of the force due to a magnetic field, we have to apply the right-hand rule or the right-handed screw rule. This is the rule used to find the direction of a vector product. The rule is very simple. Curl the fingers of your right hand from the vector V towards the vector B, because you're trying to find the cross product of V cross B. As you curl the fingers from V towards B, the thumb points in the direction of the force. Thus, we can see that the force acts in a direction perpendicular to both the velocity and the magnetic field. Now remember that the magnetic force is 0 if the charge is not moving. So magnetic field does not exert a force on a stationary charge. Now that you have seen the formula, this is obvious, because if the charge is not moving, then the magnitude of V is 0, and from the equation you can see that the force on such a charge will come out to be 0. So only a moving charge feels the magnetic force. Now we can simply find the value of the Lorentz force. Lorentz force is the force due to the electric field plus the force due to the magnetic field, and therefore when both of them are acting, we simply add up these two equations vectorially, and you will get that the magnitude of the Lorentz force on a moving charge is given by Q into E plus V cross B. So we have basically added the force due to the electric field and the force due to the magnetic field vectorially and derived an expression for the Lorentz force acting on a moving charge. Using the expression of the force due to a magnetic field, we can find the magnetic force acting on a current carrying conductor. So the first question is, what is the difference between the force that we derived in this expression and what is the difference between the force that we are going to find now? The difference is that there we had found this expression for the force on a moving charge. There was just one single charge. Now I'm trying to find the magnetic force on a current carrying conductor, and as we know, current is nothing but the movement of many charges. So for example, electric current is the flow of positive charge carriers, or you can say it is opposite to the direction of the flow of electrons. So that's the difference. There we found the expression on a single moving charge. Now we are trying to find out an expression for the magnetic force on a current carrying conductor, where this current, as we know, is made up of a large number of moving charges. Let's start by analyzing pictorially the picture of a current carrying conductor placed in a magnetic field. Let's say that I have a straight rod whose length is L and area of cross section is capital A. Now, we have seen that for a moving charge in a magnetic field, the force acting on this moving charge is perpendicular to the velocity and the magnitude of the field. In this case, we will find that the force acting on a current carrying conductor is perpendicular to the length of the rod, that is, it is perpendicular to the current I, and it is perpendicular to the field, that is B. So I say that F is perpendicular to I and F is perpendicular to B. So here we find that the force is perpendicular to the current and it is perpendicular to the magnetic field. Now let's try to derive an expression for this force acting on a current carrying conductor when it is placed in a magnetic field. So we know that the force acting on a moving charge is given by F is equal to Q V cross B. And here, instead of a moving charge, we have a current carrying conductor, which is nothing but many moving charges together. So now, instead of this Q, I'm going to write a new expression in which instead of Q, which was the charge on one carrier, I will have to write the total charge. And therefore, instead of Q, I will write the total charge which I will get by multiplying small q into the number of charge carriers that are there in this conductor. So I start by saying that let the number density of these mobile charge carriers be small n. Number density means number of charge carriers divided by volume. And therefore, if I want to simply find the number of charge carriers, I will have to multiply this n by the volume of the conductor. And in this case, it is simply L into A. And therefore, I say that the total number of charge carriers in this conductor is NLA. And each of these mobile charge carriers will have a charge on them equal to small q. I also say that for a steady current I of the rod, we can assume that each of them has a drift velocity. We have learned that charge carriers and electrons have a drift velocity, that is, current is made up of electrons moving with an average drift velocity which is given by V subscript d. So I say that in this rod, the average drift velocity is V subscript d. Using this information now, I can find out the magnetic force on a current carrying conductor. That is, instead of writing F is equal to QV cross B, I will write F is equal to, instead of this Q, I will write the total charge, that is NLA, which will be the number of charge carriers multiplied by the charge on each carrier, which will give me the total charge. And then instead of V, I write VD because this is the drift velocity of the charge carriers, and we write B as it is. And this gives me the expression for the magnetic force acting on a current carrying conductor. Remember, we found this from the same expression that we had for a moving charge, but instead of one charge, I had to write down the expression for the total charge, and instead of V, I have written VD because that's the drift velocity of the charge carriers. And now I can say that N into Q into Vd is nothing but the current density J, and we know that current density is nothing but current upon area. And therefore, if I multiply NQVd with the area A, what I get is simply the current. Now in my expression, that is equation 2, I will find these four quantities, that is N, Q, Vd and A, and replace them simply by I. And then in the bracket will remain L and B, and therefore I will get the final expression that I want, that F is equal to I L cross B. Now remember, we have made one important change in this formula. We have now made L into a vector. And what is this vector? L is a vector whose magnitude is nothing but the length of the rod itself and whose direction is the direction of the current I. So we have changed the vector notation from the current to the length in this last expression, and we get the expression that I want, that F is equal to I L cross B. So now I have two expressions. The first one is for a force on a moving charge, and the second one is for a current carrying conductor. So some points to note about the second expression is that this expression can only be used for a straight rod. Secondly, we have to remember that here we had placed the current carrying conductor in an external field. So we are not calculating the force on a current carrying conductor due to the charges which are inside the conductor itself. No, we are saying that there is already a magnetic field. In that magnetic field, we are placing a current carrying conductor, and therefore I say that B is the external magnetic field. This B in this equation is the external magnetic field. It is not the field produced by the current carrying rod. The third point is that if the wire has a random shape, what you'll have to do is break the rod or the conductor up into many such strips which are straight lines, so that you can apply this formula and then you add all these up. And if you have a continuous case, then you have to use the integral. So you can use Lorentz force even for a random shape, but you'll have to break that conductor up into straight lines so that you can use this for each of those lines and then add it all up. In order to find the direction of this force, we use the right hand rule for the cross product. Place the palm of your right hand parallel to the velocity vector and curl the fingers of your right hand from the velocity vector towards the magnetic field. When you do this, the thumb will point in the direction of the force. It is then clear that the force is perpendicular to the plane formed by the velocity and magnetic field vectors. This is the right hand rule for finding the resultant of a cross product. We will use this rule to understand the motion of a charged particle in a uniform magnetic field. We first consider the case of a particle moving with a velocity v such that the velocity is perpendicular to the magnetic field. In this case, the perpendicular force Q v cross b acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. The particle thus describes a circle if v and b are perpendicular to each other. The radius of such a circle is given by the formula mv square upon r is equal to qvb. However, if the velocity has a component along b, this component remains unchanged as the motion along the magnetic field will not be affected by the magnetic field. Since the parallel component of the velocity is unaffected by the force of the magnetic field, we apply the right hand rule for the cross product only for the perpendicular component of velocity. In this case, it is clear that the resultant force acts on the particle in the downward direction at this point. This force provides the required centripetal force. The motion in a plane perpendicular to B is as before a circular one. Thereby, helical motion is produced. If r is the radius of the circular path of the particle, then a force mv square by r acts perpendicular to the path toward the center of the circle, and this is the centripetal force. Again, the radius of this helical motion is given by mv by qb. Note, the larger the velocity, the larger is the radius and bigger the circle described. If the velocity has no component parallel to the magnetic field, then we return to the previous case where instead of helical motion, we simply have circular motion. If omega is the angular frequency, then V can be written as omega r, and hence omega, which is 2 pi V, is equal to qb by m. Here V is the frequency of rotation. The time period of revolution t is given by 2 pi by omega. The radius of the circular component of the motion is known as the radius of the helix. As seen earlier, the frequency of revolution of a particle in a combined electric and magnetic field is independent of velocity or energy. This fact is used in a cyclotron. A cyclotron is a machine used to accelerate charged particles to high energies. The magnetic and electric fields in such a machine are perpendicular to each other. It consists of two semicircular disc-like metal containers, D1 and D2, simply known as Ds because they look like the letter D. Inside the metal Ds, the particle is shielded and is not acted upon by the electric field. The magnetic field, however, acts on the particle and makes it go round in a circular path inside a D. The charged particles are released at the center P, enter the metal Ds, and each time the particle moves from one D to another, it is acted upon by the electric field. The sign of the electric field is changed alternately so that the particle is accelerated each time it crosses the gap. This ensures that the particle is always accelerated by the electric field. Each time this acceleration increases the energy of the particle, and thus the radius of the circular path increases so that a spiral path is produced. Thus the particles move in a semicircular path in one of the Ds and arrive in the gap between the Ds in a time interval T by 2. T is the period of revolution given by the shown formula. We can thus find the frequency, which is known as the cyclotron frequency, using the formula that T is equal to 1 upon Vc. Inside the Ds, the particles travel in a region free of the electric field. The increase in their kinetic energy is QV each time they cross from one D to another. Finally, they are accelerated across the Ds until they have the required energy to have a radius approximately that of the Ds. They then leave the system with a velocity v is equal to qbr upon m. Here r is the radius of the trajectory at the exit and equals the radius of the D. Hence, the kinetic energy is given as half mv square is equal to q square b square r square upon 2m. Now finally, let's write down an expression for the magnetic field due to a current element. This is known as Biot-Savart's law. Biot-Savart's law is an experimental law, that is, he found out this relationship by experimenting with current carrying wires. And therefore, we are trying to write down the magnetic field due to a current element. So remember, we are saying it is a magnetic field due to a current element, which means that it has to be really, really small. So one of the features of Biot-Savart's law is that you can apply it to only small current elements. So let's see what exactly we mean by this. We are trying to relate the current element to the magnetic field that it produces. So we are trying to find the magnetic field at a point due to a current element. So suppose you have a conductor which is arbitrarily shaped. So you say you have a conductor which has a random shape, and we know that at each point the magnetic field will be a concentric circle, the direction of which you can find using the right hand thumb rule. Now, if I want to find out the magnetic field at a point P, which is at some distance from the conductor, what I'm going to do is break this conductor up into small strips, and each of these strips will be current elements. So here what I'm going to find using Biot-Savart's law is the magnetic field at point P due to a small, that is due to one current element, which I will call as dl. So I say consider a current element dl and let the position vector of P with respect to this element be r. Finally, I say that I want to find the magnetic field dB bar due to this element, and I'm calling it dB bar because I'm finding the magnetic field at P only due to this small element. After that, I will apply the same expression to all the elements together, add it all up, and that will give me the field at P due to the entire conductor itself. So let's start by applying the Biot-Savart's law only to the small current element dl. So I find that if the angle between the current element dl and r is theta, then Biot-Savart's law says that the magnetic field at P due to a current element depends upon three factors. Now, before I tell you the three factors, I want to point out that this angle theta is created by taking the vector r and by making a tangent to the current element dl. So actually speaking, the current element is a product. It is a product of I dl. So if you want to find the direction of dl, you simply make a tangent to the conductor at dl, and the angle between r and dl is theta. So finally, I say that the magnetic field at the point P due to this small current element is directly proportional to the current I. It is directly proportional to the length of the current element, that is dl, and inversely proportional to the square of the distance r. So remember, this was an experimental law, and he found that this was the relationship between the field at a point P, and the three factors it depends upon is the current I, the length of the element dl, and the square of the distance r. So we get the formula for the Biot-Savart's law, that is, we are saying dB bar is directly proportional to I dl cross r bar upon r cube. And you can see from this formula that the direction of the magnetic field is perpendicular to the plane containing dl and r. How do I know this? Because I see that dB I can find by using a vector product of dl and r, and vector product means that the final answer will be perpendicular to each of the vectors. So we can see that the magnetic field due to a current element is perpendicular to the plane containing the current element and the position vector, that is r. So we see that dB is perpendicular to dl and r, and from this law we can write down by putting in the constant of proportionality, that is, I see that dB bar is equal to mu naught upon 4 pi I dl cross r divided by r cube, where mu naught upon 4 pi is the constant of proportionality in the SI system. So this gives me the Biot-Savart's law, and this expression is of course only when the medium is vacuum, that is when you're trying to find this in free space. And I'm saying this because the quantity mu naught is there, this quantity is only there for the medium of vacuum. Finally, I see that the magnitude, that is, this was a vector equation, but if I want to write down the magnitude of this equation, I will see that the magnitude of the field at P due to this small current element dl will be mu naught upon 4 pi I dl sine theta upon r square. This is because the vector product's magnitude will be dl r sine theta. You will cancel out 1 r from the top and the bottom, and this will give you the magnitude, that is I dl sine theta by r square. So here we have the expression for the magnitude of a magnetic field at a point P due to a small current element. And as we know, if I want to find the magnetic field at P due to the entire conductor, I'll have to add these elements all up. That is, basically integrate this expression to get the total magnetic field at point P. Now, here mu naught is the permeability of free space or vacuum. One of the most important things that I want to talk about is that Biot-Savart's law in magnetostatics, that is in this section, is basically the counterpart of the Coulomb's law. So when we were learning about electric fields, we learned the Coulomb law, and now in magnetic field, the Biot-Savart's law does the same work for a magnetic field that Coulomb's law was doing for the electric field. So let's try to compare these two laws. We saw that both of them are long range, which means that both of them actually depend inversely upon the square of distance from the source to the point of interest, and therefore we are seeing that both of them are long range. Also, we learned that magnetic field and electric fields both can be applied superposition principle, and therefore these both laws are utilizing superposition principle. That is, superposition principle is valid for both the Coulomb's law and the Biot-Savart's law. The second point to discuss is that the electric field is produced by a scalar source, that is a charge at rest. However, the magnetic field is produced by a vector source, that is IDL. Third one is that the electric static field is along the displacement vector, that is, it is along the line joining the point at which you want to find the electric field and the element, that is the charge element. So it's along the same line. However, the magnetic field turns out to be perpendicular to the current element and the position vector itself. So it was perpendicular to IDL, whereas electric field is along the line joining the charge and the point at which you want to find the electric field. Finally, remember that there is an angle dependence in the Biot-Savart's law, that is, the angle dependence is not present in the electrostatic case. Coulomb's law does not have any angle dependence, but there is an angle dependence in Biot-Savart's law. It comes from the vector product, and therefore we see that the magnetic field at any point is dependent on the angle between dl and r, and if dl and r are in the same direction, that is the magnetic field, if you want to find at any point in the direction of the current element itself, then the magnetic field will come out to be 0 because sine 0 is 0. So I say that along this line theta will be 0, sine theta is 0, and therefore the magnitude of dB will come out to be 0. So this is the comparison between Biot-Savart's law and Coulomb's law. Now let's use the Biot-Savart's law to find the magnetic field on the axis of a circular current loop. So let's say that I have a circular current loop which has a steady current capital I. As you can see, this loop lies in the YZ plane with its center coinciding with the origin. And let's say that the radius of this circular loop is capital R. Now what I want to do is find the magnetic field on the axis of the circular current loop, and as you can see here, x-axis is the axis of this loop. Now what I want to do is find the magnetic field at a point on this axis. So the first thing that I want to point out is that here I'm assuming that there are no imperfections in the shape, and so I say that the loop is perfectly circular. Secondly, I want to remind you that you can always find the direction of the magnetic field at any point on the circular current loop simply by using the right hand thumb rule. That is, you take any small current element on this circular coil. On that current element you place your hand such that your thumb points in the direction of the current, and then when you curl your fingers you will get the direction of the magnetic field. Now let's move on and find the magnetic field on the axis of the circular current loop. Let P be a point at which I want to find the magnetic field due to this circular current loop. Now let us say that we find the magnetic field at point B first due to a small current element dl. So for finding the magnetic field at P due to the whole loop, first I have to break it up into small elements, and therefore first I'm going to find the field at P due to a small current element dl of the loop. Now remember, because I have to apply Biot-Savart's law, therefore I have taken a small element so that I can apply Biot-Savart's law. So I take dl, which is a small element of the loop, and I say that the direction of dl is the direction of the current at that point, which is tangential to the plane, and let r be the position vector of the point P with respect to the current element. And finally I say that let the distance of point P from the center of the loop be x. Now I'm ready to find out the magnetic field on the axis of this circular current loop. So what I want to do is use the Biot-Savart's law. But to do that, first I have to remember that in Biot-Savart's law, for a current element, I had to use the vector product of dl cross r. And therefore, if I want to find the direction of the magnetic field induction at P due to this small current element dl, what I have to do is apply the rules of the vector product. That is, I'll have to use the right hand thumb rule to find the direction of the magnetic field. That is, take your right hand and curl the fingers of your right hand from dl towards r, and then the thumb will give you the direction of the magnetic field. And as you can see, I have then denoted the direction of the magnetic field as dB in the figure. So once I have dB, now I can use Biot-Savart's law. We already know that because the magnetic field expression includes a vector product of dl and r, it means that the field must be perpendicular to dl and r. That is, it is perpendicular to the plane created by dl and r. We can also see that in the triangle, we have a right angle triangle, and therefore small r square will be given as x square plus capital R square. This is nothing but the Pythagoras theorem, which we will need. So now if I use Biot-Savart's law at point P, I get mu naught upon 4 pi I dl cross r divided by r cube. Remember, we found the direction of the magnetic field by applying the rule of the vector product. So now I have written down the expression for the magnetic field induction at P using Biot-Savart's law. This is due to the small current element dl. Now in this case, as you can see, dl is coming out of the plane of the screen. That is, it is coming towards you, whereas r lies in the yx plane. So dl lies in the yz plane and r lies in the yx plane. And since these two planes are perpendicular to each other, it is obvious that dl and r are actually perpendicular in this case. And therefore, the dl cross r part of our formula actually just becomes r dl. So you see this theta is 90, so sine 90 is 1, and therefore dl cross r just becomes r dl, and so our expression becomes dB mu naught upon 4 pi is equal to I r dl upon r cube. R cancels, and therefore I get that dB is equal to mu naught upon 4 pi I dl upon r square. This is a magnetic field induction at point P due to the small current element dl. Instead of the small r square, I will now write x square plus capital R square using the Pythagoras theorem, and this expression I am going to use for further study. You see, we have found the magnetic field at point P only due to a small current element. However, what I wanted to find was the field at point P due to the whole circular current loop. So this is the expression of the magnetic field induction at point P due to a small current element dl. Now the direction of dB, as we saw from the vector product, is perpendicular to the plane created by dl and r, and this is obvious because dB is formed by the vector product of dl and r. Now what I want to do is find the magnetic field at point P due to the circular current loop, and therefore I'll have to add up the magnetic field due to all the elements of the circular current loop. But what we're going to do is utilize, that is, take advantage of the symmetry of the current loop. You see, the final direction of the magnetic field dB due to the current element on the top is as shown in the figure. This can be broken up into two perpendicular components, one along the x and one along the y, that is one perpendicular and one parallel component. Similarly, they're diametrically opposite to this current element right below this current element on the loop is another current element whose magnetic field will be in a direction such that its perpendicular component will be equal and opposite to the perpendicular component of the first current element, and thus you can see that the perpendicular components of the current element's magnetic field on top is cancelled by the perpendicular component of the magnetic field due to the current element below. These two cancel each other, and therefore the total magnetic induction at P due to the top and bottom elements is just the addition of their parallel components. The same argument is valid for all the elements of the loop. So we see that the net magnetic field induction at point P will just be an addition of all the parallel components of the magnetic field due to all the current elements, and parallel component of the magnetic field means the cos theta components. From this triangle you can see that cos theta will be given by r upon root x square plus r square, and we know that the final magnetic field at P is only due to the x component. So I write that dBx is equal to dB cos theta. dB's value we already know from equation 5, and cos theta we got from this triangle, and therefore only the x component we are interested in. We get dBx is equal to mu naught upon 4 pi IDL upon x square plus r square multiplied by capital R upon x square plus r square raised to half. Now this is the value of the x component of the magnetic field at point P due to the small current element, due to a single current element. What I have to do then is integrate this over all the current elements of the loop. On further simplifying this, I get dBx is equal to mu naught upon 4 pi IDL R upon x square plus r square raised to 3 by 2. Remember, this is a magnetic field induction at P only due to one single current element, because only the x component remains. That's why we are taking dBx, and we have to do this for all the elements of the loop, and therefore to find the total magnetic induction at P, you have to integrate all the parallel components. That is, you have to add up all the x components. So here I see that B, which is nothing but Bx, is the integration of dBx, and therefore when you integrate this, only dl remains under the integral because the rest are all constants, and you will see that the integration for dl goes from 0 to 2 pi r because you have to go all around the loop. This will give you a 2 pi r, and then on further simplifying you will get that the total magnetic field at point P is equal to B is equal to Bx, because only the x components add up, which is equal to mu naught I r square upon 2 x square plus r square raised to 3 by 2. And remember that the direction of this final magnetic field is along the x-axis, and therefore the unit vector I cap is the direction of the magnetic field. So this gives me an expression for the magnetic field on the axis of a circular current loop. Using this expression, we can find the magnetic field on the center of the circular current loop. All you have to do is put x is equal to 0, because x was the distance of point P from the center. But if you want to find the magnetic field at the center itself, you only have to put x is equal to 0, and thus we get the expression that B at the center of the loop, the center of a circular current loop, is given by B is equal to mu naught I upon 2R. You can also write this down as mu naught upon 4 pi into 2 pi I upon R. The reason I am doing this is because from this equation you can write many other equations if you just remember to write it in this fashion. Because now I can say that for n number of coils, that is for n such loops, I simply have to multiply this equation by n, and I get that the magnetic field at the center of n such coils will be mu naught 4 pi 2 pi n I upon r. Now remember, we have written it in this way so that we can write a general formula for finding the magnetic field at the center of a loop. So this general formula will come out to be mu naught upon 4 pi, and instead of 2 pi I will just write theta into I upon small r, where r is the radius of the loop. So now using this general formula, if you have to find the magnetic field at the center of a circular loop for other types of loops, that is other shapes, for example, if you have to find the magnetic field at the center of a semicircular arc, instead of theta you will put pi. So this is a general formula for writing the magnetic field at the center of a loop, where theta is the angle subtended by the loop at the center and r is the radius of that loop. The next thing that I want to talk about is the Ampere's circuital law. Now, Ampere's circuital law is a very useful law and is an alternative way to express Biot-Savart's law. Now, when you were learning about the electric field, first you learned Coulomb's law and then you learned Gauss's law, and you realized that both of them help you find the field, but Gauss's law was a quicker way to find the field when you have symmetry in the sum. The same logic applies between the Biot-Savart's law and the Ampere's law. Ampere's law is doing the same work that Biot-Savart's law does, but Ampere's law is faster in cases of symmetry. So basically it's the same thing, but Ampere's law is quicker in certain specific cases, as we will see. To apply Ampere's circuital law, what you need is an open surface with a boundary. And let's say that some current is passing through this surface. Ampere's circuital law says that you must break the boundary up of this surface into many small line elements, and then consider, suppose, one small element of length dl. At this element dl, you must take the length dl of this element and multiply it by the tangential component of the magnetic field at this point. So the magnetic field due to the current which is passing through the surface, at this point you take its tangential component, multiply it by the length dl, and this product you have to find for every single line element of the boundary, And then when you find this product for every single line element of the boundary, you add them all up. And this addition is done in such a way that the limit of the lengths of the elements gets smaller and smaller. That is, when the lengths of the limits get smaller and smaller, this addition becomes an integral. And this integral, Ampere said, is equal to mu naught times the total current passing through the surface. So in the simplest of words, it means that the integral of B dot dl is nothing but the product of the tangential component of the magnetic field and the length of the element, as I just stated. And we have taken an integral over a closed boundary. That is, we did it for all the line elements, which was the boundary of the surface we have considered. And on the other side, I can see that I have mu naught times I, where I is the current enclosed by the boundary, or you can say I is the current passing through the surface. And this is Ampere's law. That is the integral of B dot dl over the closed loop, which is the boundary of the surface you are considering, is equal to mu naught times the current enclosed by the loop, or the current passing through the surface. Remember, the integral is taken over the closed loop, which is coinciding with the boundary C of the surface through which the current is passing. Now, the easiest way to apply Ampere's circuital law is in cases of symmetry. And just like to apply Gauss's law, you needed to take a Gaussian surface. To apply Ampere's law, you have to take an Amperian loop. And the best cases to use the Ampere's law, like I said, is cases of symmetry. And therefore, we will stick to certain specific cases where Ampere's law can be used quickly. These cases are such that when you choose an Amperian loop, the vector B will be tangential to the loop already, or it will be such a case where the vector B is normal to the loop, or the value of B itself will vanish. These are the easiest and simplest cases to apply Ampere's circuital law. And the first case in which the B is already tangential to the loop, in this case the Ampere's law will simply reduce to BL is equal to mu naught IE. So instead of B dot dl, you will simply have BL, where L is the length of the loop itself, and IE, of course, is the current enclosed by the loop. So the first case reduces to BL is equal to mu naught IE. In the second and the third case, of course, the value comes out to be 0, because you can see that the Ampere's law contains a dot product of B and dl, and if B is normal to the loop or B itself vanishes, you'll either have cos 90, which is 0, or the value of B is 0. So that's why in the cases 2 and 3, the value of the magnetic flux itself will come out to be 0. But in case 1, that is when B is tangential to the loop, the equation will change. It will reduce to BL is equal to mu naught IE. So let's take a look at one such symmetrical example. As I said, Ampere's circuital law is basically doing the same job of the Biot-Savart's law, but can be used for a system with symmetry to give a faster and quicker way to find the magnetic field. So let's say I want to find the magnetic field due to a straight infinite current carrying wire. In this case, the Ampere's law will enable an easy evaluation of the magnetic field, just like the Gauss's law does in determination of the electric field. Let's say that I want to find the magnetic field at a point P close to this straight infinite current carrying wire. To do that, what I will do is choose an Amperian loop, and you can see that in the case of this Amperian loop, which is at 90 degrees to the current, that is, the magnetic field is 90 degrees to the current. In this case, the B is already tangential to the loop. And because B is already tangential to the loop, I can use this reduced form of Ampere's circuital law. That is, I can use the form BL is equal to mu naught IE. And therefore, in this case, instead of L, I will simply write the length of the loop itself. Remember that I could do this only because B and DL in this case are in the same direction, that is, B is tangential to the loop. If the angle was not 0, if it was any other angle, I could not use this reduced form of Ampere's circuital law. So now that I have BL is equal to mu naught IE, I simply replace L by 2 pi r, which is the length of the loop. I get B into 2 pi r is equal to mu naught IE, but instead of E, I write I, which is the current of the current carrying conductor. And this gives me the magnetic field at a distance r outside the wire, that is B is equal to mu naught I upon 2 pi r. I already know it is tangential. So I see that B is equal to mu naught I upon 2 pi r, and this is the expression that I could have got even from Biot-Savart's law, but I got it in a much faster way, basically in 2-3 steps using Ampere's law and the symmetry of the system. So thus you can see from this expression itself that the field at every point at a circle of radius r is the same, because the only thing the magnetic field depends upon is r. Everything else is a constant. Thus all points lying at the same radial distance from the current carrying conductor can be joined to form lines of constant magnetic field, and I'll get the lines of constant magnitude of magnetic field, and I'll see that they form concentric circles. So these concentric circles are nothing but lines of constant magnitude of the magnetic field. We've already seen these circles before, but now we have understood that these circles are formed because at all these points of each circle, the magnetic field is the same, and these lines are what we call as the magnetic field lines. And we can see now that magnetic field lines are actually forming closed loops. In order to determine the direction of the magnetic field due to a long wire, you have to apply the right hand rule, and it says that you hold the conductor, that is the straight wire, in your right hand in such a way that your thumb points in the direction of the current. So in this case, the current is going from bottom to top, just like it is in the figure, and in such a case, when your thumb is pointing in the direction of the current, your fingers, which are curled to hold the conductor, will give you the direction of the magnetic field. So as you can see from the figure and from my hand, the direction of the magnetic field is clockwise because the direction of the current is from bottom towards the top, and this is the right hand rule. So now we can use Ampere's circuital law to find the magnetic field due to a solenoid and a toroid. But of course the first question is, what is a solenoid? A solenoid is nothing but a long insulating wire which is wound in a helical fashion. So basically, if you want to form a solenoid, you take a cylindrical object like a rod and you wind the wire around it, and what you get is the shape of a solenoid. Let's say that the solenoid is of length L and each loop has a radius R. So of course, as in the picture you can see, you don't need a cylindrical rod. The solenoid is just a wire, but you use the cylindrical rod to sort of wind the wire around it, but the solenoid is just the wire itself. So I say that a solenoid consists of a long wire wound in the form of a helix where the neighboring turns are closely spaced. Now it is important that we assume that the neighboring turns are closely spaced. We also make one other assumption. We say that because the turns are really closely spaced, we're going to assume that each turn is circular, and therefore instead of regarding the solenoid as this helical fashion, I'm just going to say it is made up of a large number of circular loops. And why am I doing this? Because I know how to deal with a circular loop. We found the magnetic field due to a circular loop just some minutes ago, and therefore we have actually made this assumption because it's easier to look at a solenoid in the form of large number of circular loops. So this is an important assumption. The next thing that we're going to say is that if you analyze the magnetic field of a solenoid, you will see that the net magnetic field, which is going to be the vector sum of all the fields due to all the turns, you'll see that in the middle there is some gap, that there is an empty space. This is because the field between two neighboring turns tends to vanish in this gap, and therefore you see that there is empty space on the top and bottom where the turns are close to each other. The next thing is that if you take a look at the field and the interior midpoint that is really well inside the solenoid, and you look at an interior point P, you'll see that the field is uniform, strong, and along the axis of the solenoid. So how do we know it's uniform? Because the lines are equally spaced. It is strong and it is along the axis of the solenoid. Finally, we are also going to say that the field at the exterior midpoint Q is weak, that is, at any point outside the solenoid, the field is weak, and moreover, it is along the axis of the solenoid, as you can see. So basically, the field doesn't have any perpendicular component, it's completely parallel at this exterior midpoint Q, and actually, for the sake of our argument, we're going to assume that the field outside the solenoid is 0. So we're going to say that because the field approaches 0, we will assume that the field outside is 0. We're making this assumption to find the magnetic field due to a solenoid, and therefore I say that the field inside is parallel to the axis everywhere. That's also an assumption we're making, that it's parallel to the axis everywhere, and we're assuming that outside it is 0, which means that to make the derivation, that is to find the magnetic field of a solenoid, we are going to look at a really small section as shown by this green rectangle. We are actually focusing only in this small section of the solenoid, because in this section we are assuming that the magnetic field is parallel along the axis everywhere. This is a good assumption only for this interior section, and of course outside we have assumed that the field due to the solenoid is 0. So now let's start to find the magnetic field due to a solenoid, but to do that we have to first amplify this section and we have to take an Amperian loop. That's the procedure to apply Ampere's circuital law. You have to take an Amperian loop. So here you can see we are taking a rectangular Amperian loop A, B, C, D, and we are going to analyze the magnetic field due to this solenoid on the sides of this rectangle ABCD. So let's take a look at what is happening. You can see that along CD the field will be 0 because we just said that we're assuming the field outside the solenoid is assumed to be 0. So since CD lies outside the solenoid, we're going to say that CD has no field along it, and therefore the field along CD is 0. If you take a look at the sides AD and BC, you will see that these sides are perpendicular to the field, and since the field is only along, say, the x direction, there is no field along y direction. So you see this is the case where the field is normal to the Amperian loop, and therefore there's going to be no contribution of AD and BC to the Ampere circuital law. So again we have to ignore AD and BC as well, which means the only thing that is valuable to us is the side AB. And let the field along AB be B, which is shown by the green arrow. So the green arrow is the field B, and you can see it is exactly along AB, and this is the case where the field and the element, that is the current element or the element of the Amperian loop, are in the same direction, and therefore we can use that reduced Ampere circuital law. So let's say that the length of this side AB is h. Therefore the effective length that will be useful to me for Ampere circuital law is equal to h. And now when I use the Ampere circuital law, I will use the length h. One other thing to remember is that we need to know what is the enclosed current by this loop in order to find the magnetic field, because we need to apply the enclosed current inside Ampere circuital law. So what is the enclosed current? Let's say that the number of turns per unit length is given by small n, and then we are only considering the turns which are fitting inside this length h. So if you're only looking at the turns which fit inside this length h, then it means that the total number of turns inside this length h will be n into h, because n is number of turns per unit length. So now obviously I can say that the enclosed current is then I into nh, where I'm assuming that I is the current in each loop, and because there are nh such loops, I will say that the total current is INH. So now I have the total enclosed current and I have the effective length. I can apply Ampere's circuital law, which is nothing but the reduced form here I'm using because B is along the effective length. So BL is equal to mu naught IE can be written as B, where B is the magnitude of the field along AB, into, instead of L I'm going to write H because H is the effective length, is equal to mu naught, and the enclosed current instead of I will be I into NH. So here I have BH is equal to mu naught I NH, and as you can see H and H cancels and I get the final formula, that is B is equal to mu naught Ni. Now I want to make one comment here. Here I have found the magnetic field along AB, which means I am looking at the magnetic field at a point well within inside the solenoid. So well within the solenoid, the magnetic field is mu naught Ni. This is not the magnetic field outside the solenoid, which we have assumed to be 0. This will, or at a point close to the solenoid, which will again be different. This is the magnetic field at a point which is well inside the solenoid. So now we can also apply the same method and procedure to finding the magnetic field inside a toroid. So again, what is a toroid? A toroid is a hollow circular ring on which a large number of turns of a wire are closely wound. So you can sort of think of a solenoid, and you can think of it, instead of being open at both ends, you just close it, that you have a closed solenoid, an endless infinite solenoid, and that's a toroid. So a toroid, as you can see, is a hollow circular ring on which a large number of turns of a wire are closely wound, and we can see that this toroid is carrying a current I in each of its rings. And now I will apply Ampere's law to actually find the magnetic field due to the toroid, and I'm saying that the magnetic field in the open space, that is either inside point P, which is also not lying on the toroid, or at point S, which is in the exterior, again not lying in the toroid, we will see that for both these Amperian loops, the magnetic field will come out to be 0. So what we do is we actually take 3 Amperian loops. We take one which is inside, that is at P, so that's loop 1. We take at a point Q, which is inside the toroid, so that's the loop 2, and we take a loop 3 which is exterior to the toroid, that is at a point S outside the toroid. So here I have 3 Amperian loops, and I want you to remember that when you were applying Ampere's circuital law, when we discussed the procedure to apply Ampere's circuital law, we saw that we had to take not just a loop, but we had to take a surface, and then when we are writing the enclosed current, or when we are writing the current, we have to ask, which current is cutting through this surface. So even though I have not shown the surface here, remember the current that you have to assume is the current which is cutting the surface of the loop. So if you can see carefully, loop 1 does not cut any currents at all. Loop 2 obviously cuts the current, and loop 3 also cuts the current because the surface inside loop 3 is cutting the current. So remember, you have to think of the current as the current which is cutting the surface which is enclosed by the Amperian loop. So let's start by finding the magnetic field along the Amperian loop at point P. So let's look at loop 1. The magnetic field along loop 1 be B1 in magnitude. Remember that the magnetic field along the loop will be the same and is tangential to the loop. So here I can quickly apply Ampere's reduced circuital law, that is BL is equal to mu naught IE, where L is nothing but the circumference of the loop, that is 2 pi R1, where R1 is the radius of this loop. And of course then the question is, what current is it enclosing, or the better question is, what current is cutting the surface created by this loop? And as you can see, there's no current in the surface that is being cut because of the surface of loop 1, and therefore the IE in this case is 0. And from this then, if I apply Ampere's circuital law, I'll simply get that B1 is equal to 0, which means that magnetic field at a point P, which is lying on the inner side of the toroid, is going to be 0. So now let's take a look at what will be the magnetic field at a point S, which lies in the exterior of the toroid. And again, as I have predicted that this is going to be 0, let's see if this is true. So first of all, let the magnetic field along loop 3 be B3. And once again, from Ampere's law, the effective length will come out to be 2 pi R3, where R3 is the radius of this loop 3. So this is the effective length, and therefore B into L will become B into 2 pi R3. But the more important question is, what is the current that is being cut by this surface? So imagine the surface that this loop is enclosing, and you will see, if you pay attention carefully, that the surface enclosed by this loop 3 will cut the current twice. So therefore I say that each turn of the current carrying wire is cut twice by the loop 3, and because of this, what happens is that the current coming out of the plane of the paper, that is the current coming out of the Amperian loop, is cancelled exactly by the current going into it, and therefore overall this surface is cutting no current. So the current coming out of the loop and current going into the loop is exactly the same. They are being cancelled by each other, and therefore again IE comes out to be 0, and consequently B3 comes out to be 0. And this is very important to understand. Finally then, we will find the magnetic field inside the solenoid at the Amperian loop 2, and here let's say that the magnetic field magnitude is B. Now let's consider the effective length. The effective length again will be the circumference of this loop. Let's say R is the radius, so the effective length will be 2 pi R. And now the bigger question is, what is the current being cut by the surface of this loop? You'll see that each turn of the current carrying loop is cut once by the loop 2, because only one direction of the current is being cut by the surface. The other direction is not included in our Amperian loop 2, and therefore in this case you can see that the current will be cut through the surface, and therefore there will be some answer to IE. It's not getting cancelled, it's not going to go to 0. So in this case I say that the current enclosed is N into I, where I is the current in each single circular loop of the toroid, and N is the number of loops that are along the toroid. So here I can say that Ampere's circuital law reduces to B into 2 pi R is equal to mu naught Ni. This will give me B is equal to mu naught Ni upon 2 pi R, where N is the total number of turns. Now I can actually simplify this equation. I say that if R is the average radius of the toroid and small n is the number of turns per unit length, then I can just write capital N, which is the total number of turns, as 2 pi Rn, and therefore I can say that the total number of turns is equal to average perimeter of the toroid into the number of turns per unit length. And then in this case, instead of the capital N, I will just write 2 pi Rn. So I get mu naught 2 pi Rn into I upon 2 pi R, and as you can see 2 pi R cancels, and you get mu naught Ni, and this is nothing but the magnetic field due to a solenoid that we saw before, and thus you can see that the magnetic field due to a solenoid and the toroid well inside their structures is the same. It comes out to be mu naught Ni. So next thing we want to find is, what is the force acting between two parallel currents? So the first question is, what do you mean by parallel currents? Parallel currents means that the direction of the current must be parallel to each other. This could be two straight current carrying wires, this could be two straight current carrying rods, etc. Of course, then you will ask, why would there be a force acting between two parallel currents? And the answer to this is that we have already seen when you place a current carrying conductor in a magnetic field, it will experience a force. In fact, we also found an expression for this force, that was I L cross B. So we already know that if you place a current carrying conductor in a magnetic field, this current carrying conductor is going to experience a force. That's point one. The second point is that we also know that each current carrying conductor will produce a magnetic field, and we also found an expression for this magnetic field using Biot-Savart's law. In fact, it came out to be mu naught upon 4 pi 2 I by R. So we know two things. One, if you place a current carrying conductor in a magnetic field, it's going to experience a force, and two, each current carrying conductor is going to produce a magnetic field in the region around it. So now if you carefully take a look at these two current carrying conductors, let's say A and B, if you look at these two current carrying conductors carrying currents IA and IB, then think about what is happening. For example, if I study only one of them, then I'll see that the magnetic field due to the first conductor, let's say that the first conductor is A, there will be some magnetic field due to the first conductor A, and this magnetic field will be like the external magnetic field for the conductor B, and therefore I say that this magnetic field will actually affect the conductor B. So now the conductor B is placed in a magnetic field, and this magnetic field is created by the first conductor. So I am saying that the conductor A produces the magnetic field BA at all points along the conductor B. So if you only look at B, it's like keeping a current carrying conductor in a magnetic field, and we know how to find the force on this current carrying conductor. So obviously now you understand why there would be a force in the first place, because B is like a current carrying conductor being placed in a magnetic field. The only difference is that in this case the magnetic field is created by another current carrying conductor. So again we can use the right hand rule to tell us the direction of this field, and you will see that the direction of the field is inwards as shown in the figure. To find the force acting on conductor B due to the conductor A, I have to apply the formula F is equal to IL cross B, but also I need to know what B is in the first place. So B is nothing but the field produced due to A. So first I'm going to write down the answer to the magnitude of the magnetic field produced due to conductor A. That's given by Ampere's Circuital law, and the expression for that magnitude is mu naught IA upon 2 pi D. So remember, this is the magnetic field created due to the conductor A, and we are going to use this magnetic field as the external magnetic field for finding out the force acting on B. So now I can say that the conductor B which is carrying a current IB will experience a sideways force due to the field BA. You can find the direction of this force using Fleming's left hand rule, and the magnitude of this force is IBL into BA. So as you can see, IB is the current of the current carrying conductor. Here we are looking at the second conductor, that is the B conductor. So I've written IB, L is the length of the conductor, and BA is the field acting on the conductor B, which is the field of the conductor A. So here I have the magnitude of the force, and I can see that the direction of this force is towards the conductor A. So we have the direction and we have the magnitude. Here BA of course will be replaced by the expression on the top. So this will come out to be FBA is equal to mu naught IAIB upon 2 pi DL. So this is the force acting on B due to A, which as you can see is towards A. A similar argument of course can be made for the reverse scenario, where I'm going to try to find the force acting on A due to B. You see, current is flowing through B as well, and therefore B will create a magnetic field and A will be affected by this magnetic field, and therefore force will act on A, and we will see that this force is being acted on A towards the conductor B. And here again the effective length is L, and therefore the force comes out to be equal and opposite to the force exerted on B by A. So here you see FBA is equal to minus FAB. So finally I can say overall that if you have two parallel currents, that is you have currents in the same direction, then they will attract each other. So currents flowing in the same direction attract each other, and by the same argument you will find that currents flowing in opposite directions actually repel each other. Now you can see that this is quite opposite to the thing that happens in terms of electrostatics. That is, in electric field, firstly you look at charges, and these charges attract each other if they are opposite and repel each other if they are the same. However, in case of currents, you have two currents and they attract each other if they are the same and repel each other if they are opposite. So this is opposite to the laws of electrostatics. And finally, I want to define the same force in terms of the force per unit length. So instead of FBA, I want to write it as it in terms of small f, where FBA represents the magnitude of the force per unit length. Then I simply have to remove the length from the expression and I get FBA is equal to mu naught IA IB upon 2 pi d. This is the force per unit length acting on each of these conductors. The reason I'm writing it as the force per unit length is because this is used to define the ampere. The ampere is nothing but the current flowing through each of these conductors when they are placed 1 meter apart and a force of 2 into 10 raised to minus 7 Newton meter per unit length is acting on each of these conductors. In such a case, the current flowing through these conductors is said to be an ampere. So because the definition of ampere requires a force per unit length, we define this force in terms of its unit length. A rectangular current carrying loop, when placed in a uniform magnetic field, experiences a torque. It does not experience a net force. We first consider the case when the rectangular loop is such that the uniform magnetic field B is in the plane of the loop. This field exerts no force on the two arms AD and BC of the loop. This is because the force on a current carrying conductor involves the vector product of the vector L and B, and since they lie in the same direction for the arms AD and BC, the force on these arms comes out to be 0. The force on the arm AB of the loop is perpendicular to the plane of the loop and exerts a force F1 in magnitude on it. This is directed into the plane of the loop. F1 is equal to I small b into capital B, where small b is the length of the arm AB. Similarly, it exerts a force F2 on the arm CD and F2 is directed upwards. F2 and F1 are equal in magnitude because the arms CD and AB are same in length. Thus, F2 is also IB into B. Since the forces are equal and opposite, the net force on the loop is 0. However, because they don't lie along the same line of action, there is a torque on the loop due to the pair of forces F1 and F2. This torque tends to rotate it anti-clockwise. This torque in magnitude is given by the formula tau is equal to IAB, where A is the area of the rectangle. If the plane of the loop is not along the magnetic field but makes an angle with it, we take the angle between the field and the normal to the coil to be equal to theta. In such a case, the forces acting on the arms AB and CD, which we will call F1 and F2 as before, are equal and opposite and have a magnitude F1 equal to F2 equal to IBB just as before. Thus, similarly, they will still result in a couple. However, the forces acting on the arms BC and DA are equal and opposite as well. But here, these forces act along the same direction. Because they are collinear, they cancel each other, resulting in no net force or torque. Thus, as the previous case, the torque tends to rotate the coil. This torque created by the forces F1 and F2 is less than as compared to the earlier case when the plane of the loop was along the magnetic field. This is because the perpendicular distance between the forces of the couple has decreased. The torque in this case comes out to be IAB sin theta. Using the expression of torque in both the cases, we can write down a general formula for the torque on a rectangular loop. We do so by defining the magnetic moment as IA. Rewriting the formula for torque as a vector product between the magnetic moment and the magnetic field, we get that torque can be expressed as one expression, that is tau is equal to m cross B. The moving coil galvanometer is nothing but an instrument used to measure small electric currents, and it is based on something we have just learnt. That is, it is based on the principle that if you place a loop that is a coil in a magnetic field, it's going to experience a torque. So the principle of the moving coil galvanometer is that a loop placed in a magnetic field experiences a torque. So what is the basic parts of a moving coil galvanometer? As you can see, there is a magnet, there's a coil, there's a spring, and therefore I say that the galvanometer consists of a coil, and this coil has many turns. This coil, of course, is free to rotate about a fixed axis, and that's what's going to happen. The torque is going to rotate this coil about a fixed axis, and we have placed this in a uniform radial magnetic field. And as you can see, in order to create this uniform radial magnetic field, there is a soft iron core. So this makes the field radial and also increases the strength of the magnetic field. Finally, when the current flows through this coil, a torque acts on it, and we have found the expression that the torque is given by NAIB, where N is of course the number of turns, I is the current, A is the area of the loop, and B is the strength of the magnetic field. The magnetic torque NIAB is what will rotate this coil. So when this coil will rotate, the pointer which is connected to the coil will move, and it will give us the measurement of the current that we are trying to measure. So it will give us the value of the current that we are trying to measure. And of course, to get a steady angular deflection, there is a spring SP, and this spring provides a counter torque given by K phi that balances the magnetic torque NIAB such that the deflection is steady and smooth, and therefore in equilibrium K phi is equal to NIAB. So basically the pointer will not move due to any other random interferences. It will remain steady because the spring has tension in it and it's holding the pointer in its place. So you get K phi is equal to NIAB in equilibrium at any point along the measurement scale. So from this I can get the K, which is the torsional constant of the spring, and I get phi is equal to NAB upon K into I. Now, the moving coil galvanometer can be used as an ammeter. So, of course, you already know what is an ammeter. An ammeter measures currents and a galvanometer also measures currents. So, what is exactly the difference? The moving coil galvanometer measures really small currents and it's a very sensitive device. But we can use a moving coil galvanometer as an ammeter. But how do we do that? We have to make some changes in order to use a moving coil galvanometer as an ammeter. So the first question is how to do this. The galvanometer cannot as its own be used as an ammeter because of two reasons. The first one is, like I said, the MCG or the moving coil galvanometer only measures small currents, and therefore its full scale deflection, that means its maximum range, is only a few microampere, whereas ammeters are used to measure larger currents. So that's why we cannot just directly use an MCG as an ammeter. And the second reason is that because the MCG itself has a very large resistance, there could be a change in the value of the current in the circuit. So you don't want to affect the current that you're trying to measure. So because you don't want to change the current value that you are trying to measure, what you do is you take another resistance and you place it in parallel to the galvanometer, and such a resistance is known as shunt. So in general, if you are placing a resistance in parallel to an instrument such that most of the current passes through this resistance, then such a resistance is known as shunt, and this shunt resistance of course will be very small so that most of the current will pass through S and the galvanometer will be safe, plus the galvanometer will not affect the current that you are trying to measure. So here, as you can see, that when the current will enter this entire instrument, Ig will pass through the galvanometer and the remaining I minus Ig will pass through S, because S is shunt, it has a small value, so most of the current is passing through S. So now I can see that as resistances S and G are parallel, the potential difference across G and across S will be exactly the same because they are connected between the same 2 points. And then I can say that Ig into G will be equal to Is into S, where Is is nothing but the current I minus Ig. So I get I minus Ig into S is equal to IgG. From here I get the value of S, that is what is the value of the shunt resistance that I need. S is equal to Ig upon I minus Ig into capital G, where capital G of course is the resistance of the galvanometer, internal resistance of the galvanometer. Now I can also define the current sensitivity of the galvanometer. It is nothing but the deflection per unit current, that is phi upon I. Phi I know is NIAB upon K. I just took I to the other side, so I get phi upon I, which is the current sensitivity of the galvanometer, to be NAB upon K. A convenient way then to increase the sensitivity of this ammeter will be to increase the number of turns N. Now I can also use the moving coil galvanometer as a voltmeter. Now what does a voltmeter do? It measures the voltage in a circuit. So I can use the moving coil galvanometer as a voltmeter, but again I can't directly use it as a voltmeter. Why? Because of two reasons. So this is because the voltmeter has to be connected parallel to the portion where you want to measure the voltage. If you see how you always measure the voltage, you connect the voltmeter in parallel. So what happens is that we want this voltmeter to draw a very small current, otherwise the voltage measurement will disturb the original setup by a large amount. So to ensure this, we place a large resistance RS in connection, that is in series with the galvanometer. So here, to convert the MCG into a voltmeter, a resistance is connected in series with the resistance of the galvanometer. So the total resistance, of course, is RS plus RG because it's a series combination. Now you can see very easily from Ohm's law that V is equal to G plus RS into IG, where G plus RS is equal to V upon IG, and here I can just say that RS is V upon IG minus G. Knowing V, IG and G, value of RS can be determined. So here you can find the value of the series resistance, which you must connect with the galvanometer to convert it into a voltmeter. Voltage sensitivity is defined as the deflection per unit voltage, that is phi upon V. Now phi I know is NIAB upon K. I simply divide that by V and I get phi is equal to NAB I upon KV, or I can write this as NAV upon K into 1 by R because I upon V is 1 by R. So this is the voltage sensitivity. One final thing to remember is that current sensitivity is not directly connected to voltage sensitivity. So current sensitivity increases does not mean the voltage sensitivity may increase. So keep that in mind. Finally, you can see that if you want to convert the MCG into an ammeter, you need to connect a resistance in parallel, but if you want to convert the MCG into a voltmeter, you need to connect a series resistance. So this wraps up all the concepts that I want to cover under the umbrella of magnetic effect of electric current. I hope you enjoyed watching this video. Thank you for watching and stay tuned. Hi guys, thank you for watching this video. If you like our channel, please subscribe by clicking on the link here. And if you want to get your very own target book, you can click here. Till then, keep watching for new videos on our channel and stay tuned for more updates.